Hello students, greetings of the day. Till now we discussed about gravitational force, gravitational field intensity and gravitational potential energy. Now it is time to know about Kepler's laws of gravitation. These are the three famous laws which can describe planetary motion and the motion of satellite. So let us get started. Let us start the study of Kepler's law, which describes motion of a planet, that is Earth, around the Sun. These all can be studied with the help of Kepler's law. Kepler's law as stated like following. The first is law of orbit. As it is written here, each planet moves around the Sun in an elliptical orbit with the Sun at one of the foci. Let us consider this be the orbit of a planet which is an elliptical orbit. Sun has to be at one of the focus. So if these are the two focus, Sun let it be here. Now this axis of ellipse, as you know, is known as minor axis, and this other axis is known as major axis. Now if this major axis can be written as A and this minor axis as B, then distance of focus from the center can be written as E times A, where E is called eccentricity of the ellipse. Eccentricity is ratio of the distance SO to AO. If at a given moment of time this be the position of planet, then its position vector with respect to Sun can be given by the vector r as shown here. So this is our first law, which only states about how is the motion of planet around Sun and where is the location of Sun. The second law is law of areas. It states that the line joining the Sun and a planet sweeps out equal areas in equal intervals of time. Let us consider this again. This being the elliptical orbit, this is location of one of the foci where the Sun is there, and it is the location of a planet at a given moment of time. Let this position vector is written by r. Now let us consider a small interval of time, let that be delta t. So if planet is having velocity v1 here, the distance it travels in time delta t can be written as v1 delta t. Here we have considered the time interval to be small, so speed v1 can be assumed constant for the time interval delta t. Now the new location of planet has become this one. According to the law, the line joining the Sun and the planet sweeps equal area. So let us see what is the area swept by the position r in time delta t. It can be written as you can see, this is very close to a triangle. So the area in time delta t can be written as it has to be half into the base is v1 delta t multiplied with r. So this is area swept in time delta t, and if this is to be constant, then we can say that v1 r1 is constant, or we can say that v is inversely proportional to r. So when planet is here, which is at a larger distance from the Sun, then its speed has to be relatively less than what its speed will be when it is at this position. Let us represent the position by q, because this time r is having a small value, so of course v2 has to be more, and from here we can write v1 r1 to be equal to v2 r2. If you multiply with mass on both the sides, then we can say that angular momentum about Sun is constant. This is nothing but the angular momentum conservation. So the second law of Kepler is derived with the help of angular momentum conservation, which states that since there is no external torque acting on the Sun-planet system, so angular momentum of planet has to be conserved, and we can write mv1 r1 to be equal to mv2 r2. It can be written in vectorial form as well. L1 can be written as equal to L2. So this is conservation of angular momentum or the law of area given by Kepler. Both are same. One more thing you can derive from here, that if we have to write rate of change of area, that is known as areal velocity, then it can be written as angular momentum upon 2m. So we can calculate, if it is required, the areal velocity of the planet, that should be equal to angular momentum upon twice of mass. The third law is law of periods. It states that the square of the time for a planet to complete a revolution about the sun is proportional to the cube of semi-major axis of the elliptical orbit. This is saying about the semi-major axis. Now, let us see what is this semi-major axis. Just now I had explained it. This one is called semi-major axis. I had written by the symbol A. So, now we can write that square of time period is proportional to cube of this distance A. Let us see how this is true, and for simplicity, if we consider the orbit to be circular, then we can write velocity of a planet can be given by under root g mass of sun upon r. This I have taken from the fact that gravitational pull will provide the necessary centripetal force for the planet. So we can write g ms m upon r square to be equal to mv square by r. On solving this, we will get value of v to be equal to under root g ms by r, and time period can be written as it is 2 pi r upon v. Let us substitute the value of v, that will be equal to 2 pi r upon under root g ms upon r. If I square both the sides, that will give t square to be equal to 4 pi square upon g ms and cube of r, which verifies the statement of Kepler's third law. Of course, here we have verified it for circular orbit, but it can be verified even for elliptical orbits. To verify it for elliptical orbit, we have to start from the relation that we had derived earlier for rate of sweeping area by position vector of planet with respect to sun. But generally, from numerical point of view, this one is sufficient because we get numerical mostly from the assumption that orbits of a planet are circular. Let us now do this for elliptical orbit. Generally, our purpose will be solved only with circular orbit, because mostly you will get questions from circular orbit. But if it comes from elliptical orbit, then let us see how it can be solved. We have to write first the second law, which states that dA by dt is equal to L upon 2m. Now, as you can see, center of ellipse is taken as origin. We can write coordinate of the focus, where we are assuming the sun is positioned to be equal to minus AE0, and this being the semi-minor axis B, the whole distance can be written as twice of B, and this distance is equal to 2a. Now, if we consider R1 and R2 are the shortest and the farthest distance of planet from sun during its motion, which can be given as R1, of course it has to be here, and R2 when it is here. So let velocity at this point when it is at the shortest distance be v1, and velocity when it is at the maximum distance is v2. We can write R1 to be equal to a1 minus e. This is from the property of ellipse. Similarly, we can write R2 to be equal to a1 plus e, where e is eccentricity. Now, from geometry we know that the relation in semi-major axis and semi-minor axis can be written by b is equal to a root under 1 minus e square. As we have considered v1 and v2 be the speeds of planet at the minimum and the maximum distance from Earth, so from conservation of momentum we can write mv1 r1 to be equal to mv2 r2. Also from energy conservation we can write half mv1 square minus gmsm upon r1 to be equal to half mv2 square minus gmsm upon r2. So on solving equation 1 and equation 2 and taking help of relation between A and B and values of R1 and R2, finally we will get T square to be equal to 4 pi square upon GMS into A cube, which is the original form of Kepler's third law, that is law of periods. So here we have derived it both for circular and the elliptical. For most of our purposes, this circular derivation itself is sufficient to solve the question, especially for JEE mains and Neet level. Let us now see some illustration based on these three laws. The first illustration is the time period of Jupiter is 11.6 years. How far is Jupiter from the Sun? If distance of Earth from the Sun is given 1.5 into 10 to the power 11 meter. So if we write time period of Jupiter, that has to be equal to 11.6 years. Its distance from Sun is not given, that we have to calculate. I am writing the distance by Rj. Now time period of revolution for Earth is equal to 1 year, as we know, and radius of orbit of Earth is equal to, that is written by Re, 1.5 into 10 to the power 11 meter. Now we can make use of the third Kepler's law, which states that square of time period is proportional to cube of the radius. So we can write Tj square upon Te square to be equal to Rj cube upon Re cube, which on solving gives Rj to be equal to Re Tj upon Te whole to the power 2 by 3. If we substitute the values, that will come out to be 1.5 into 10 to the power 11, 11.6 upon 1 to the power 2 by 3, that is equal to 7.68 into 10 to the power 11 meter. So this distance is distance of Jupiter from the Sun. The next illustration is the mean distance of Mars from the Sun is 1.5 to 4 times that of the Earth from the Sun. Find the number of years required for Mars to make one revolution about the Sun. Again we can apply the third law, that is T square is proportional to cube of R. So if we write it for the Mars and the Earth, then it can be written as T1 square, where T1 I am writing time period of Mars, upon T2 square, where T2 is time period of Earth, that should be equal to R1 cube upon R2 cube, where R1 and R2 are distances of Mars and planet Earth from the Sun respectively. Now from here T1 upon T2 will be equal to R1 upon R2 and this whole to the power 3 by 2, which gives T1 to be equal to T2 R1 upon R2, this whole to the power 3 by 2. Now let us substitute the values. For Earth time period is 1 year, so 1 multiplied with distance, it is given that Mars is at a distance 1.5 to 4 times that of Earth. So it can be written as the ratio 1.5 to 4 and to the power 3 by 2, which on solving will give 1.88 years. This is time period we got for revolution of Mars around the Sun. One more illustration is there. Let the speed of the planet at the perihelion P in figure be Vp and the Sun-planet distance Sp be Rp. This location is called perihelion, which is the shortest distance from the focus. So this location P is called perihelion. Relate Rp, Vp to the corresponding quantities at the aphelion, which is Ra and Va. Now as you can see, A is the farthest distance from the Sun. Also it is asking, will the planet take equal times to traverse BAC and CPB? Okay, let us do this. Now as it is given in the diagram itself, we can refer to the figure, and then Rp and Vp are, this should be Rp and Vp has to be in this direction, it should be Vp, and in this direction has to be Va. So we can see that Rp and Vp are perpendicular to each other. Similarly, Ra and Va have to be perpendicular to each other. So if we apply the law of conservation of angular momentum, we can write Mp, Rp, Vp to be equal to Ma, Ra, Va. From here we can write, because mass has to remain same, so we can write Vp upon Va to be equal to Ra upon Rp. And since Ra is greater than Rp, so we can write Vp has to be greater than Va. This is the first part where we have to relate Rp and Vp to Ra and Va. Now in second part it is asking what will be the time taken to traverse BAC and CPB. Now see, since area SBAC, if you see it is the area SBAC is greater than area SCPB, so and aerial velocity of planet has to be constant around the Sun, that is, it will sweep equal area in equal times. Hence, the planet will take longer time to traverse BAC than it will take for CPB, because for the portion BAC, speed has to be somewhat lesser than what it is for the section CPB. And we can say the time for section BAC will be more than the time for the section CPB. So this is our second part also completed. Now this is very important and very interesting topic, which is different paths of a projectile. Now we are going to see what will be the path taken by a projectile if it is taken to a height h above the Earth's surface and then is given a velocity v. So let us see, depending on the value of v and the direction of v, we can predict different types of satellite motion. So let us start with, first we have to consider that this is the Earth, the radius being r, and the satellite has been launched at a height h, that is projected at a height h. Now depending on what the speed it is having, its distance we can consider from center of Earth to be small r. Now first I am considering the case if imparted velocity v is 0. Simply it has been taken to the height h and then put there. Then of course the satellite will move towards Earth's surface, and then motion has to be in straight line with of course the variable acceleration. So here the motion will be straight line towards the center of Earth, and it will fall at the surface of Earth. Now second case, if you consider where this v is less than the orbital velocity. Orbital velocity is the velocity with which, if it is projected, it will start orbiting around the Earth. We will see in our next session what its value has to be. But if VO is the orbital velocity and the satellite has been projected with velocity less than v, of course in direction shown like here, then the path will be elliptical. The particle will strike with the Earth's surface. It will be like this. Will come here, strike the Earth's surface. But path has to be elliptical. So if I draw the whole ellipse, it will be like this, where center of Earth has to be at one of the foci. The next case, if we consider if v is less than v0, but this time the velocity imparted to satellite is greater than what it had for the case 2, then again the path will be elliptical, touching the Earth's surface. Okay, let me draw it separately so that this will be easily understood. For case 1, it has come straight down to the surface of Earth. This is our part 1. For part 2, the ellipse will be like this. This is the second case. The third, this time it is having this much of velocity. Again, path is elliptical, but it is just touching the surface of Earth. So this is the third case, here being the center of Earth. Now if v is equal to v0, this is the velocity with which it is projected is equal to the orbital velocity, then motion will be circular. It will revolve around the Earth in circular orbit. So this is our path 3, where the motion is completely circular. This is our path 3. And the orbital velocity is also known as first cosmic velocity. Next, we have to consider the case if v0 is less than v and less than ve. This time the velocity with which the satellite is projected is having value more than orbital velocity but less than the escape velocity. In next session you will see what is escape velocity. Here just as it has been mentioned, so I am simply briefing about this escape velocity, that it is the velocity with which if a particle is projected, it does not return to that point. That is known as escape velocity. We will see in detail later. So if the projected velocity is more than orbital velocity but less than escape velocity, then again the path will be elliptical. This time the Earth will be at first foci. So again this is elliptical. This is our path 4. Now Earth has come to the second foci. The next we have to consider when v is equal to escape velocity. This time the particle will move in parabolic path and will escape from the Earth's gravitational field. So it will move like this and escape. The next and the only remaining case can be when v is more than the escape velocity. Of course, this time also it will escape from Earth's gravitational attraction and will be having some non-zero velocity with which the particle will be moving in interstellar space or interplanetary space. So these are the all cases with which a projectile can be projected with different velocities and the path taken by the projectile in all the cases. Now I have one more numerical example. A satellite of mass m, that is 1000 kg, revolves with velocity 10 km per hour in an elliptical orbit around Earth. The distance between Earth and the satellite is 1000 km and angle between radius vector and velocity vector is 150 degree at a certain moment. Find out angular momentum of satellite about Earth. Let us first draw the situation. It is the elliptical orbit in which satellite is revolving and Earth has to be at one of the foci. Now let us consider the planet at any given moment of time is here, which I have shown by point P, and it has position vector with respect to the position of Earth, that is given by r. Its magnitude is equal to 1000 km. Now as we know that velocity always should be tangential to the path, so this will be the direction of velocity. Now what is angle given between radius vector and the velocity? That is given here as 150 degree. So if this is 150 degree, this angle can be written as 30 degree. Speed is also given, which is equal to 10 km per hour. And this distance being equal to 1000 km. Now we have to calculate angular momentum of satellite about Earth. As you all know L vectorially can be written as R cross P. From here we can write magnitude of L to be equal to, it should be R cross mv, and of course mod of this, that will be equal to mvr sine theta. Theta is angle between the velocity and the vector r, which is given here 150 degree. So let us now substitute all the numerical values. It will be 1000 into 10 into 5 by 18. I have converted it to meter per second, multiplied with 10 to the power 6. That is the value written in meter, and then sine 150 degree. The value will be equal to 1 by 2. So on solving this, final answer will be 1.4 into 10 to the power 9 kg meter square per second. This is the angular momentum of satellite about Earth. With this, our today's session is complete. Let us look forward to the next session, where we are going to discuss different kinds of satellite of Earth, whether it is natural or an artificial one, and how different terms, that is time period of revolution, energy of satellite, escape velocity, how these things can be calculated. Till then, please take very good care of yourself. Goodbye.